Good morning, ladies and gentlemen. Pause the video and do this now in your notes.
A car sitting at a red light accelerates when it turns green. If it takes 6.4 seconds to get to 16.5 meters per second, what is its acceleration?
Go!
You can do this. Come on, do this.
All right, now that you have done the problem, have you done it? Pause it, for real. Okay, let's do this. Information mining first. A car sitting at a red light accelerates and it turns green if it takes 6.4 seconds. Okay, so 6.4 seconds. That's my time. It takes 6.4 seconds to get to 16.5 meters per second. Meters per second. That is velocity. What is its acceleration?
What's that equation for acceleration, Ms. Moore?
Okay, acceleration equals v final minus v initial over time. Okay, there's these letters down here, right? I don't have any letters on here. So it says...
You only have one velocity,
and
too.
I only have one velocity, but what does it say? It says a car sitting at a red light. So it's chilling, right?
It's just sitting there.
In the beginning, initially, it's just going 0 meters per second.
So that other one must be...
V final. Let's plug this stuff in. 16.5 meters per second minus 0 meters per second divided by 6.4 seconds. And that gets me 16.5 minus 0 divided by 6.4, and I get 2.58. I'm gonna put it right here. 2.58, and we're talking about acceleration. Let's see, I've got meters per second.
Okay.
All right, so let's move on here. Now that we've refreshed our acceleration skizzles. So in our last video, you guys rolled the ball down the track of 0.8 meters. It looks something like this over here.
In fact, it's exactly like this over here.
And we rolled the ball, 0.8 meters was right here, we measured it, and we let go of it, we rolled it down, and we timed it, right? It says compare your prediction with the measured time for 0.8 meters, explain your results. So if we remember our results, if we think back and look in your notes and recall what your results were, you'll notice that it didn't take 2 times the time to go down.
It went twice as far.
It went twice as far, but it did not take twice as long. Weird, huh?
I know.
Why is that? Well, let's come back to acceleration. As the ball is moving down the track, in fact, let's just do it again. You can hear that it accelerates, going faster and faster. Because it's accelerating down the track, that time is, well, it's shorter than double. Does that make sense?
Yep.
All right, so we know the velocity at the start is 0. Oh, did I miss a slide?
No, that's good.
We know the velocity at the start is 0 when we first let go of the ball, right? That initial velocity, 0. What can we do to find the final velocity at the bottom of the track? So I know that this initial velocity right here is 0. Okay, 0, right, because I'm holding it.
You haven't let go of it yet.
And then, oh yeah, I haven't let go yet. And then I let go right now. What is the velocity right at that point? How can we do this?
What can we do to find that without any digital electronic devices?
Motion diagrams use dots to show positions and arrows to show displacement and velocity.
We did motion diagrams the last time.
We did. Shall we go to page 55 and 56?
Yeah.
Okay. Oh yeah, that's what we did last time, right? Okay, 55.
56.
Boom. Okay, let's
The
look.
next page.
Oh, 56. Once more. Come on. All right, let's take a look at this diagram right here. And we said that motion diagrams, that's this, with the dots and the arrows, use dots to show position and arrows to show displacement and velocity. So the bigger the arrow gets, the bigger the velocity and the displacement. So it's moving a very small amount here and going a slow velocity. And as we move along, the arrow gets bigger, which means it's moving more distance because it has a faster velocity.
Oh, so it's accelerating.
It's accelerating.
Woo!
Think back to our car. And then you can see it starts to slow down here a little bit, right? And oh, look at the acceleration arrows.
Oh.
Acceleration is increasing. Acceleration is decreasing. Okay. Then what page? 55? Not through that one, huh?
No.
Okay. Moving right along. The diagrams on page 56 use arrows to show changing velocity. So the longer the arrow, the faster the velocity. The shorter arrow, shorter velocity. The simple diagram on page 46 may be appropriate to describe motion on the track and the table. So let's come back over here. 46, back to our lovely motion diagram with dots.
A, B, C, and D.
So we already talked about these motion diagrams here, right? When we rolled the ball across the track, it worked with this guy right here.
Yep.
And then when the ball went down the ramp, it looked like this guy right here.
Oh, yeah.
Yeah.
Okay.
Okay. The ball accelerated down the track, but goes at a constant velocity on the table.
That sounds very important to me.
It is very important. Write this down. Write everything down. You should be writing this down. Start the video over if you're not writing anything down. Okay. So on page 46, like we just looked at, we saw that as we, let me go back to the slide real quick. When the ball was going down the track, it was that letter C. And then as it was on the table with constant velocity, it was that letter B.
I think so.
Yeah. Okay. Draw a sketch in your notebook, in your notes. Make a motion diagram on the table and the track. Draw
So
this.
what dots are best to show what's going on in the track, and what dots are best on the table? They should be able to do this. You don't have to show them.
All right, moving right along then.
Track, table. Track, table. Track, table.
This again? Acceleration definition. So we can describe acceleration lots of different ways. Yesterday we drove the car around and we saw that the arrow went up, the arrow went down. This on the speedometer. It went up fast, it went up slow. It went up slow, it went down fast, right?
Yeah.
And so we can describe acceleration in different ways. This is an equation that we can use to describe acceleration. And just like a sentence, you can read it, you can put numbers in it, and we can get our calculation, we can get our answer. So, we know the velocity at the start is 0. Remember when I put the ball at the top and I'm holding it? It's not moving yet, right?
Right.
What can we do to find that final velocity at the bottom of the track?
Oh my goodness.
How can we do that? Set up meter sticks on the table. Find the speed of the ball on the table.
Ah. Here are meter sticks.
Yeah, let's get that to look good here. All right, so first, good thing I've got this flannel. Don't do it at home, ladies and gentlemen. All right, so it says find the speed of the ball on the table. What was the equation for speed again?
Distance over time, I think.
D over T.
Right.
So we have to find distance, so on the table, and the time that it takes for the ball to go on the table.
Miss Moore, how long is a meter stick?
That's a great question. It's 1 meter long.
Thus the name.
I'm gonna go ahead. Should I just put that in right now?
Yeah.
Yeah, so put 1 meter up top, divided by, let's get the time. How do we get the time? When do we start the timer?
Well, when it gets on the table, you want to find the speed on the table, you got to get the speed when it's on the table.
Right there to there, okay.
Yeah.
Turn it on, reset it. Okay, start, stop, start, stop. Start at the 0.8 meter mark. And I got 1.02
Okay, that's
seconds.
all right.
Okay,
So
can we do this math real quick?
I wish you would.
To find the speed on the table. 1 divided by 1.02. And it's almost 1, right? 0.98 meters divided by seconds.
So now we've got how fast the ball was going when it rolled 1 meter across the table.
All right, so what is next? Know the speed of the ball on the table. What else do you need to find the acceleration on the track?
What else do you need?
So we know the table. We're trying to figure out the acceleration of the track. Okay. How can we figure out our acceleration? So, okay,
What do we know for sure?
We know for sure that it starts from rest,
Yeah.
right? So we need to figure out what these two are. Don't forget, this is the acceleration down the track. And we already have the speed on the table. How are those related? Instantaneous velocity is what the speedometer in your car tells you. When I said, look at my speedometer after 3 seconds, and it was like 15 miles per hour, that was my velocity at that instant. My instantaneous velocity at the start for this lab is gonna be 0 meters per second. We know
Yeah.
that, the starting velocity. What we're trying to find this, our final velocity at the very, very end, the instantaneous final velocity at the end.
I bet some of these kids have a pretty good idea.
You know who you are. If you know, you know. Acceleration uses instantaneous velocities. So over here, we have to use instantaneous velocities with acceleration. Instantaneous velocities.
At that particular instant.
At that very instant, acceleration uses instantaneous velocity. Let's practice. Why not? On a 1/4 mile drag strip, a race car accelerates from 0 to 300 miles per hour in 5 seconds.
That's really fast.
What is the acceleration? Pause the video, do it, give it a go. Okay. Seriously, pause the video. Okay, here we go. So we know we've got this number, 300 miles per hour. Miles per hour, and that's miles per hour, that's velocity. Okay. And then we've got 5 seconds, that's the time. And it wants to know the acceleration. What does it say? What does it start from? From 0.
Ah,
So again, whenever you're calculating acceleration, you cannot use the average velocity. You must use instantaneous velocity. We know at the very beginning, at that instant, the velocity was 0 meters per second. And at the very end, after that 5 seconds, for just that moment, his velocity was 300, or her velocity was
Could be,
300.
could be, could be.
You just don't know. 300 miles per hour. So let's do this. Velocity final minus velocity initial over time. These must be instantaneous. I'm running out of room here. The velocity final was 300 miles per hour minus. I love it when it's just minus 0. It makes my life easier. 5 seconds.
what is 300 divided by 5?
300 divided by 5. I don't even need a calculator for that. If you need a calculator, do it. Ain't no shame in the game. Oh shoot, miles right there. Miles per second. Sweet.
Miles per hour.
Oh shoot.
Oh!
Miles per hour. Good catch, good catch.
And then. No,
Guys,
no,
I'm
that-
a creature of habit. Make sure you read per second. There we go. miles per hour right here, second on the bottom. If you caught that before I did, good job. Like, Miss Moore, you're doing it wrong. Oh, another one. Okay, a baseball pitcher winds up, takes 1.2 seconds. What is the ball's acceleration if it leaves his hand going 40.0 meters per second? We're talking about the same stuff? No, different units here.
So basically, you're leaving that fraction bar up there because it's going to be the same with just different numbers, yes?
Yeah, because it wants to know what the acceleration is again, right?
Yep.
Okay, so pitcher winds up and takes 1.2 seconds. What is the ball's acceleration if it leaves his hand going 40 meters per second? So it leaves his hand, that's at the very end, right?
Yeah.
So 40 meters per second. And when you start, it's going
0.
well, meters per second. Okay, so 40 goes here.
One of these days, we got to have a velocity that's not 0 at the start.
No, we're gonna have to.
It's coming, I promise.
We'll have to mix that up. Okay. 40 divided by 1.2. 1.2, and I get, drum roll please.
Boom.
33.3 meters per second
Okay.
Right?
This stuff is easy. However,
Do not use average velocity to calculate acceleration, you guys. These are the velocities at that very instant, at that 0 second, at the very beginning and at the very end after 1.2 seconds. Do not give me an average velocity. Don't give me distance over time. We don't want to use that. Acceleration is calculated using instantaneous velocities.
good Lord, how many times do we have to say it?
Oh, it's supposed to be the fourth time, and it's going to happen a few more times.
Yeah.
And you notice how it says V2, V1? Same thing,
Yep.
right? Average velocity is useful only when velocity is mainly constant.
Okay.
Did we have velocity? Was velocity constant over here earlier?
Wait a minute, I think there was something. I remember something about being constant. That's a great hint.
Eerie. Draw another sketch in your notes. Label where velocity is constant and where it is changing.
Go ahead.
Track,
Go ahead.
table, do it.
Da-da-da, da-da-da, da-da-da-da.
Okay.
Right.
There we go. What equation can you use to describe the motion on the track? Write it on the track.
What do you mean on the? Oh, on that previous sketch.
Yeah,
Okay.
on your sketch. Yeah, not on my track. What equation can you use to describe the motion on the table? Write it on the table.
Go back to that slide. So on the track would be right here. What equation can you use? We've only been using 2 here today.
And then on the table, what equation can we use on the table? If you're confused, look back at your motion diagrams from the beginning. If you didn't do those, start over and try again. Okay, moving on here. Oh, we just did that one. Let's break it down now. The speed on the table would equal the final velocity of the ball at the bottom of the track. Think about that.
That makes sense, doesn't it?
Think about it.
That makes sense over here. Because what's the ball doing while it rolls down the track?
So as it's rolling down the track, it's accelerating, right?
Yeah.
And it's getting faster and faster and faster and faster. And right there is as fast as it will go the rest of the way. So if we can just figure out what the speed is from here to here in that certain amount of time, then can't we then we can know that that whatever that speed is the final velocity. So if we want to find the acceleration on the track, What else do we need?
I think we need the time.
Yeah.
What time though?
Well, we're talking about the acceleration on the track, right?
Yeah.
So we need the time on the track.
Okay.
Let's do it. On. Reset. Oh, I'm gonna use my right hand. Third time. Okay. And ready? Set. Right there. And I got, this time, 1.72.
You need to identify that as a time on the track.
Mm-hmm. So time on the track, 1.72 seconds.
So,
So,
what should they do now?
That's a good question.
I think you should just turn them over, turn them loose.
Calculate average acceleration. You have everything that you need.
Sweet.